Hola, chaps. Let's learn. Hola, chaps. Mr. Turek here. For Honors Aerospace, it's my hope to have you learn some physics and engineering calculations along the way. And so I've come up with this force vectors PowerPoint from Project Lead the Way, and I kind of want to step you through it. So let's get started. In order to do calculations of truss structures, we have to deal with vectors. And so let's get into what it means to be a vector. There are two types of quantities in the calculation world. A scalar is an object that only has magnitude. An example would be this calculator has a mass of 200 grams. It's just a magnitude. A speed of 5 miles per hour. A position, a distance that I walked of 5 miles today. A vector is a quantity that has both magnitude and direction as well. So an example would be if I am 8 meters west of the flagpole. So how many meters? 8 meters, that's my magnitude. What direction? The direction west from a reference point. So that's an example of a vector quantity. Velocity is also a vector quantity. So if I said I was going 18 miles per hour east, that would be a vector. If I only said I was going 18 miles per hour, that would be a scalar. Speed is a scalar. Velocity, speed with direction, is a vector quantity. Force is a vector quantity. So if I push with 10 newtons down on this table, that would be a vector. All right, and moment, which we're going to get into, is a twisting force. It can be clockwise, it can be counterclockwise, and that direction is the magnitude, how strong the twisting force is, that's the magnitude of it. All right. The way we represent vectors is generally with an arrow most of the time. And here's notation where they have a capital letter with an arrow symbol on top of it. And it really depends on what instructor that you deal with. I've taken many math courses at different universities, and each instructor tends to have their own style about how they represent a vector. This is Project Lead the Way, and there you have it. Oops, sorry. So when we draw a vector, we can do it as a arrow that represents both the magnitude and the direction at the same time. So this is 3 units long, and it's at 30 degrees above the positive x-axis. So let's see what it says, magnitude of 3. Whatever the units are on that scale, we don't know. Could be meters, could be inches. And the direction is the direction that the arrowhead is pointing. So a vector has an arrowhead and a tail as well. The tail is where it intersects the positive x-axis. This direction is 30 degrees counterclockwise measured from the positive x-axis. Yes, you would normally say all that. The sense of this is just putting it into one of four quadrants and saying, well, it's going up and to the right. So that would be the sense of this, upwards and to the right. And so you can imagine the other three choices are down and to the right, up and to the left, down and to the left. So Project Lead the Way wants you to be able to express the sense of it. Your calculator, by the way, doesn't know the difference between up and to the right and down and to the left as far as calculations go. So be aware that you need to keep your sense about you as you do this engineering stuff. So here's an entire slide dedicated to just saying that. Up and to the right, that would be down and to the right, down and to the left, up and to the left. See, I'm not hiding anything. All right. Of course, and to be able to correctly do this stuff, you need to be able to do trig. And so this slide is an excellent review of what you need to be masters of. When you have a right triangle, the sum of all the angles adds up to 180 degrees. One of the three angles is 90 degrees. So that means theta, the angle shown on the bottom left of this right triangle, has its complement in the upper corner of this triangle, upper vertex of this triangle. So theta plus the other angle must add up to 90 degrees because the right angle is the other 90 degrees for the total to add up to 180. Pythagorean's famous theorem says the hypotenuse squared is equal to the length of the adjacent side squared plus the length of the opposite side squared. Now, there is a generalization of this when the angle is not 90 degrees. C squared equals A squared plus B squared minus 2AB cosine C. However, the cosine of C is 0, and so that general formula reduces down to Pythagorean's theorem when the angle C is equal to 90 degrees. And I see I need to go like this. And I think I'm trying to go forward. There we go. So you guys should have memorized this as SOHCAHTOA. And of course, in my upbringing, my math teacher gave us a mnemonic memory device based on Oscar and his old aunt. But you can come up with your own version of this. So SOHCAHTOA. Sine is the ratio of the opposite side to the hypotenuse. It's a dimensionless number. It's a ratio. Cosine is the ratio of the adjacent side to the hypotenuse. And tangent is the ratio of the opposite side to the adjacent side. So opposite divided by adjacent. Opposite divided by hypotenuse. Adjacent divided by hypotenuse. And I'm covering up something that says what I just said. The sine of the angle theta, in this case, is the ratio of the opposite side, whatever value it might be, divided by the hypotenuse. And there's certain triangles that you should have memorized in math class. For example, if the opposite side has a value of 1 and the hypotenuse has a value of 2, then the sine of theta should be 1/2, and that corresponds to an angle of 30 degrees, or pi over 6 radians. Cosine, of course, is the ratio of the adjacent to the hypotenuse. And tangent is the ratio of the opposite side to the adjacent side. So tangent is also the sine divided by the cosine, since the hypotenuse would cancel out. Of course, you need to be quick on your calculator and able to do this for values provided or figure it out on your own. Let's see if they give us an example. Hypotenuse is the magnitude of the force. And in this figure, it says the adjacent side is the x component of the force, and the opposite side is the y component of the force. So I often refer to the facts and the phi, but that's particularly for the applied force. All right, so now what? The sine is the ratio of the opposite to the hypotenuse. Cosine is the ratio of the adjacent force divided by the hypotenuse, the adjacent component of the force. The tangent is the ratio of the opposite component to the force divided by the adjacent component to the force. And if it's not in the first quadrant, then draw it respectively in its second, third, or fourth quadrant. Whoops, I kind of clicked ahead too fast. So it says, suppose I have vector A, and its magnitude is 75 pounds, and its direction is 35.0 degrees counterclockwise measured from the positive x-axis. So the sense of it, of course, is going up and to the right. Now, what are the values of the magnitudes of the x and y components? So on your calculator, make sure that you have it set for degrees, not radians, because the angle is being given to you in units of degrees. And on your calculator, to calculate the adjacent side, you would go 75 pounds times the cosine of 35 degrees. Calculate what you get. Also, while you're at it, calculate the length of the opposite side. Let's see. I suppose if I were to zoom in on this and set the shading just right, you would probably get the same result as me, right? Let's set this up like this. All right, so for example, clearing my screen, if I go 75 pounds times the cosine of 35 degrees, I'm getting a result of 61.436403 pounds, and you should round that to 3 sig figs and call it 61.4 pounds. For the opposite side, 75 sine 35 degrees, and I get 43.0 pounds. So let's see what they do here on this PowerPoint. There's the math, cosine, there's SOHCAHTOA, and this is just for cosine. It's the ratio of adjacent to hypotenuse. So the adjacent side is hypotenuse times the cosine of theta, and you plug it in, and you get the same result I did, 61.4 pounds. For the opposite side, it's the hypotenuse times the sine of 35 degrees. So I'm taking the expression for sine being the ratio of opposite divided by hypotenuse. I'm multiplying both sides by the hypotenuse, and that isolates the opposite side. So opposite side is equal to the hypotenuse times the sine of the angle. Hence the result, 43.0 pounds. All right, so your turn. What if it's going at 35 degrees clockwise from the positive x-axis and still it has the same magnitude? So when it says your turn, go ahead and pause this tape and calculate what your answers should be. That was your excuse to pause right there. All right, so not all of you paused. Anyways, you should get the same magnitudes for each of the two legs, but the sense now is to the right and down. So what does that mean? That means the x component is going to be positive still, but the y component is down instead of up, and down is the negative direction, not the positive direction. So the sign will change. Instead of being 43.0 pounds, that's going to switch to becoming negative 43.0 pounds. And yes, the signs matter. So here's the same positive result as before. And here's the negative result. Now, how did they plug in 35 degrees down? You have two choices. Either you keep your sense about you and you realize that the down direction is negative and you manually add the minus sign that your calculator didn't give, or you revert to the math circle and say, I'm going to go completely around the math circle. And so 0 degrees is the positive x-axis, 35 degrees is up here, 90 degrees, 180, 270 degrees, 330 degrees is too far. That would be negative 30 degrees. So you have to back up and call it 325 degrees. So if you type in 75 pounds times the sine of 325 degrees, then on your calculator, which I suppose you can see, or not, did I do it? I did it wrong. Okay, so 75 times the sine, let me clear this. All right, so 75 times the sine of 325 degrees, enter, and there's your minus sign, negative 43.0 degrees. So your calculator can work only if you give it the angle expressed on the math circle from 0 to 360 degrees. And of course, it can handle above 360 degrees and below 0 degrees, but you need to keep your sense about you about what is correct. All right, so here's a diagram that shows a boat being pulled out of the water onto the grass, and there are two people pulling on this boat. Person A is pulling with a force of 75 pounds at an angle of 35 degrees up and to the left in the orientation of this piece of computer screen, where up means towards the top of the screen. And to the right, I said to the left, of course that's to the right. Person B is pulling with a force of also 75 pounds, also at an angle of 35 degrees, but in this situation, 35 degrees down and to the right instead of up and to the right. So what is the resultant force of these two people pulling? That means what is the vector sum of these two arrows? Now, in a math class, you might learn how to add vectors together graphically by actually connecting head to tail and head to tail. I don't know if I happen to have a program that does that. So let me look for a moment on my thing, and I actually do. So I have a program called Vector, and when I run this vector, it asks me, so how many vectors do I have? And I would say, yeah, I'm going to calculate the resultant. And I have two vectors, and I'm to put it in the order of magnitude and direction. So for vector A, the magnitude is 75 pounds, and the direction is 35 degrees. And for vector B, the magnitude is 75 pounds. And for the direction, I can't put in 35 degrees. I probably can put in negative 35 degrees, although I've never done that. Let's try it now and watch what happens. Yeah, so it works. Okay, so this program, which you could code yourself, uh, scales the vectors to fit on your graphing screen. And I need to go just a little bit more. There we go. All right, and it labels it. Here's vector 1, starts from the origin, because that was the first vector I gave it. And then you connect vectors graphically by drawing head to tail, using a compass to maintain the correct direction. So this is going at 35 degrees above the x-axis. And now I connect vector 2. The tail of vector 2 is drawn starting from the head of vector 1, and it's going at 35 degrees below the positive x-axis, where the axis is shifted to the head of the previous vector. And the resultant vector, when I click on this, will go directly from the tail of the first vector drawn to the head of the last vector drawn, no matter where it might be. And so here it's labeled and it's in green, and you can kind of see that it ends up going along the positive x-axis. Now, there's a logical reason for that. Person A is pulling upward to the right with some force, so we actually calculated it already. Person B is pulling downward with the same magnitude force that person A is pulling up. And really, it's not up and down like up into the air. It's really up like north on the compass map and down like towards south on the compass map, because this entire problem takes place with a bird's eye view looking down on the ground from above the boat. So one person's pulling north with some magnitude, and person B is pulling south with an equal magnitude. So the net effect is they cancel out as far as north and south goes. Now they're both pulling east. So the resultant vector is twice the magnitude of the east component of vector A. And this program displays that value and says, oh, so the resultant magnitude is 123 pounds, and the direction is 0 degrees. If I could scroll over enough for you to actually see that on the screen. And I think now you can see my entire calculator display screen. All right, so back to the PowerPoint from Project Lead the Way, and they're going to the trouble of doing this algebraically, and they're resolving each vector into its two components. So person A was pulling 43.0 pounds north and 61.4 pounds east. Person B was pulling 43.0 pounds south, or if you like, negative north, and 61.4 pounds east. And so when you add together the x components, it doubles, and you're going to end up with 162.8 pounds. They're going to round to 8 when they do it. And here I didn't round off till afterwards, so mine would actually round up to 0.9. And as far as north and south goes, they cancel out. The resultant is the vector sum of the forces. And there you can see they rounded off afterwards as well, got 122.9 pounds. So the magnitude is 122.9 pounds. The direction is 0 degrees from the positive x-axis, and the sense is to the right. Now, this program that I have can show you that graphically, the order in which you do the addition of vectors doesn't matter. So if I were to run the same program again and say, oh, yeah, I'm going to put in two vectors, and yes, I remember it's magnitude first, enter, then direction, enter. Suppose I put in vector B first, and I say, well, it's 75 pounds, but vector B is negative 35 degrees, and I put that one in first. And then vector 2 was also 75 pounds in magnitude, but now it's positive 35 degrees in direction. What does it look like? Well, there's vector B drawn first, because that was the first one I put into the program, and it's going east and south. And then vector 2 was person A, because that was the second one I typed into the program, and it's going east and north. And sure enough, the resultant doesn't change. So this is a property of the graphical addition of vectors. The commutative property of addition applies. And you might remember from math class, the commutative property means A plus B is the same thing as B plus A. Now for vector addition, commutative property holds. And that's good news for you because it means the order in which you add the vectors together isn't going to change what the answer is. And so one thing you should do, just like this calculator program, when you are done figuring out each component, you should draw one final vector that represents the resultant vector. In this case, it has a magnitude of 123 pounds. The direction is 0 degrees, measured from the positive x-axis. The sense is to the right, and you should draw that and say, that is the resultant vector. There it is shown on this PowerPoint. It has a magnitude of 122.9 pounds, and the direction is along the positive x-axis. Here's a drawing from POE. It shows a wall that has a hook fastened into the wall, and two cords are fastened to the hook. One of them is labeled vector C and has a magnitude of 300 pounds, and is making an angle of 60 degrees with the positive x-axis off to the right on the screen. Vector D has a magnitude of 400 pounds and is pulling at 30 degrees below the positive x-axis. So what is the sense, magnitude, and direction for the resultant force? If I were to use my handy dandy vector program, then of course I could just type it in that way and get the answer. You are not going to have the advantage of using this program, so I suppose I should just shut my calculator off for a moment. I'll have to come back to it to work out these results, but here's what you do step by step. You build a table. In fact, instead of just clicking on the PowerPoint to show it to you, let me see if I can use this computer screen and sort of guide you through the process that I would do. And then we click on the computer screen and have it confirm what I'm sharing with you. So I'm trying to get this contrast to look good for you, and that seems reasonably good. All right. So for vectors, what I would do is I would build a table, and the table would have three columns in it. The first column would be what vector am I working on? And I'm going to work on vector C first. And the second column would be what is the x component of that vector? And I would get that by calculating the cosine function of the hypotenuse for that angle. And the third column would be the y component for that vector, and I would use the sine function to calculate the component of that vector. So vector C is 300 pounds at an angle of 60 degrees. So to calculate the x component is equal to the hypotenuse times the cosine of the angle. So I would be typing in 300 pounds times the cosine of 35 degrees. And on my calculator, 300 pounds times the cosine of 35 degrees. Go ahead and pause and calculate it yourself before I finish it. Yeah, okay, you didn't pause. I get 245.7 pounds. 245.7 pounds. For the y component of vector c, so all this is vector c, it would be the hypotenuse times the sine of the opposite of the, of the angle. In this case, angle theta that's given. So the hypotenuse is 300 pounds, and the sine of the sine of 60 degrees, you may have memorized in math class, it would be the radical 3 over 2, which would be 0.866 times 300. You have a calculator. You could just use your calculator. 300 sine 60 degrees, enter. By the way, I see I put in the wrong number for the first one. Looking at my screen, I see used the angle of 35 degrees when this problem says the angle is 60 degrees. So let me go fix that as well. So for the y component, I currently have 259.8 pounds. So I'll write this one down. 200, what did I say? 59.8 pounds. For the x component, realizing I typed in the wrong angle, I will now correctly type in 300, at least I hope correctly, sine 60, I'm sorry, cosine 60. By the way, the cosine of 60 degrees is 1/2. So I expect the answer to read 150. Bloop, it does. 150 pounds is the x component of vector c. So I'm spreading this out over 3 or 4 rows because of my mistake, but normally I would do this on one row. I wouldn't bother writing the formula again. I would just write the value. Here, let me demonstrate with vector d. So vector d says it is 400 pounds at an angle of negative 30 degrees. And so for the x component, I recognize that the cosine of 30 degrees is radical 3 over 2, which is 0.866 times negative 400. I have a calculator. Let's just use it. So 400 cosine negative 30 degrees, enter, and it says 346.1 pounds. So 346.1, and you're asking, well, where's the minus sign? Actually, it says 346.41. So 346.4 pounds. Well, the cosine function is called an even function about 0, and that means that the plus value of the cosine function has the same value as the minus value of the cosine function. The cosine of positive 30 degrees has the same value as the cosine of negative 30 degrees. The sine function is an odd function, and the sense reverses as you go through 0 symmetrically. So the sine of 30 degrees is the negative of the sine of negative 30 degrees. Go figure. And while we're at it, the sine of 30 degrees is 1/2. And therefore, for vector d, if you want to bother using your calculator, you're going to type in 400 sine 30 degrees, enter. And sure enough, you should end up with 200 pounds. Okay, so this table that I've just built shows every vector, in this case, there's just 2 of them, every vector resolved into its x and y components. Now, here's the trick about vectors. The vector in any one direction is independent of the vector in the perpendicular direction. That is just great. So whatever I do horizontally is independent of whatever I do vertically. And whatever I do going east-west is independent of whatever I'm doing going north-south. Imagine if you were on the Earth at Cerritos and you wanted to get to the North Pole and you tried to get there by walking east, and you keep walking east and you keep walking east and you keep walking east and you get to the Atlantic Ocean, and then you swim across the ocean, always going east, and then you walk east and then you swim across the Pacific, and then you're back in Cerritos, and for all that walking east you got absolutely nowhere closer at all to the North Pole, which is in a direction perpendicular to east. Okay, so that means you add together each column independently. And this first column is what I will call the resultant vector. So I write R for that. For the X column, I see I have 150 pounds from vector C and 346.4 pounds from vector D. Add them together. And so I have a 0.4. These are all going to be in units of pounds. 6 plus 0 is still 6. 5 plus 4 is 9. And 3 plus 1 is 4. So I have 496.4 pounds in the X direction. Now, separately, I add together the vectors in the Y direction. In the Y direction, for vector C, I had 259.8 pounds, and for vector D, I had 200 pounds. I add them together, and I get a resultant of 459.8 pounds. These represent the X and Y components of the resultant vector. So if I were to draw with a sketch, I would draw a vector pointing to the right with a magnitude of 496.4 pounds, and then draw a vector going up that's a little bit shorter and label that 459.8 pounds. And then, hey, they are perpendicular to each other. That means they form two legs of a right triangle, and the hypotenuse is the resultant. So the magnitude of this resultant vector is the x component of the resultant vector squared plus the y component of this resultant vector squared. Take the square root of that afterwards. And so on your calculator, second square root of 496.4 squared plus 459.8 squared. Beep, 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 beep. And it says the magnitude of R works out to be 676.6 pounds, which now you could round off and say, well, okay, 677 pounds. But wait, there's more. A vector is a magnitude and a direction. So you're not considered done if you just tell me what the magnitude is. You are obligated, you're required to also tell me what the direction is. And for the direction, we're asking you, what is this angle formed between these two vectors? For that angle, you now know the lengths of the hypotenuse, the opposite side, and the adjacent side. So you can use any of the three trig functions to solve for that angle. You'd be taking the inverse trig function to get the angle. My personal preference is, given that the hypotenuse is slightly rounded compared to the two legs that go into it, I prefer taking the inverse tangent of opposite over adjacent. The TOA says the tangent of the angle, which you can't see, okay, TOA means the tangent of theta is equal to the ratio of the opposite side divided by the adjacent side. Well, great. What I know is the opposite side is 459.8 pounds. I know that the adjacent side is 496.4 pounds. So how do I get theta from that? The answer is you have a button on your calculator that takes the inverse angle of the ratio. So if I give it the ratio of opposite divided by adjacent, first of all, before I put it into my calculator, I want to have an expectation of what I'm going to get as an answer. First of all, make sure your calculator is in degrees and not radians. Secondly, recognize there are certain angles that you're supposed to know. One of the most common angles that you're supposed to know is for a 45-degree right triangle. For a 45, 45, 90 right triangle, the sides have the same length, and the hypotenuse is the square root of 2 longer than either of the two sides. That's at a 45-degree right triangle. In this particular problem, my opposite side is slightly shorter than my adjacent side. So I'm expecting my calculator to give me an answer that is a little bit less than 45 degrees. If I don't match my expectation, it means either I'm not thinking correctly, or I put it into my calculator incorrectly, or I've made some kind of math mistake that I need to check. You should also be mentally doing this expectation before you turn on your calculator. So now, with that expectation, I go inverse tangent, and I type in 459.8 over 496.4, close parentheses, enter, and sure enough, if you can see it, it says 42.8 degrees, matching my expectation that it's supposed to come in a little bit less than 45 degrees. You are obligated to include that in your answer, 42.8 degrees. Let's get back to the PowerPoint and see how they teach you all this stuff. So here they are, slide by slide. The first vector, C, is 300 pounds, and they resolve it. So any vector, even one that your grandmother gives you, can be safely broken into two perpendicular vectors. In this case, vector C is being broken into an x component perpendicular to a y component, and the given angle theta is 60 degrees. Using trig, the hypotenuse times the cosine of theta gives you the x component of that hypotenuse. Using trig, the sine component of the hypotenuse, I should say the hypotenuse times the sine of theta, will give you the opposite leg of this right triangle. And they're rounding it off, unlike what I did, and calling it 260 pounds. Great. This is vector C resolved into its x and y components. I would write this down in a table and say, okay, column 1 is vector C. Column 2, 150 pounds. Column 3, 260 pounds. And that one row is for that one vector. Next vector, next row. Vector D, 400 pounds at negative 30 degrees. X component would be the hypotenuse times the cosine of the angle, 350 pounds. Y component would be the hypotenuse times the sine of the angle. Because it's down, this is going to be a negative result, negative 200 pounds, which you can just make out. All right, so what they're showing here is they're taking the two original vectors, C and D, resolving them into their components shown by these red vectors. And they've drawn them to some form of scale that shows the y component of vector C is greater in magnitude than the y component of vector D. So overall, in the tug of war in the y direction, C is going to win. In the x direction, both vectors are pulling to the right, so the resultant is going to be much farther to the right than either one is individually. And if I move my screen out of the way, there is nowhere that is truly out of the way. It shows here's the x and y components, here's the x and y components, and you've got to take into account that a negative direction means you have to subtract it, or if you like, add it as a negative quantity. And like me, they should end up with the x column being added together separately from the y column, sum of the forces. Beep, beep, beep. The result is a very strong force off to the right because they're both pulling to the right, and a much smaller force in the upward direction, meaning I goofed on my work. Oh my goodness. I'm not going to reshoot this video. Instead, I'm going to point out to you that I did not take into account that it is negative 200 pounds in the y direction on my work. In fact, I can back up right now and show you my mistake is right here. I'll even use the red pen of death this time to say, look, that is a mistake that cost me points and caused the bridge to fail. This was negative 200 pounds in the y direction for vector D. And of course, that means the resultant is 59.8 pounds, not what I had before. And the angle is, and all of this is wrong. So basically, my entire result, everything after that one mistake is wrong. So this became wrong, that became wrong, and good thing that Project Lead the Way has a PowerPoint slide where they did it correctly. And now you can say, ha, Mr. Turek, if I pointed that out to you in classroom, I would have deserved extra credit. And you're all right. So let's finish off the Project Lead the Way PowerPoint. And the sense is going up and to the right, much like your understanding of engineering over time. Here's the two components. Last step is draw them to scale and recognize that because they're at right angles to each other, they form two legs of a right triangle. And you can use Pythagorean's theorem to calculate the hypotenuse and inverse tangent to calculate the angle. And here they're just showing graphically the commutative property of vector addition holds, and therefore the long vector plus the short vector gives the same result as the short vector plus the long vector. The order of operations of adding them doesn't matter. You get the same hypotenuse. And they get 500 pounds. And you have to calculate the direction as well. And my image is blocking your view, opposite over hypotenuse. Now clearly here, this is going to be much, much less than 45 degrees. That is a skinny angle. That is less than 30 degrees. I can't tell you how small, but definitely well below 30 degrees. And click, and it's 7 degrees. It looks skinny. That's reasonable. The sense is counterclockwise from the positive x-axis. I should really say the sense is up and to the right. And they're going to do that one more time. There you have it. The sense is up and to the right. Okay, I'm hoping that now you've become masters of doing this. This ends the slideshow. I have much more I want to cover with you, but this is already long enough video for this time. So what I'm going to do is send this off to you. All right. Good luck.